In this assessment, we're asked to calculate delta H for the reaction shown on screen. I've gone ahead and made a list of the bonds broken and formed in this particular reaction. And we'll note that we're going to be breaking a primary CH bond at this carbon here. And we're going to be breaking a hydrogen carbon bond to a methyl group in the molecule CH4. We'll be forming the primary carbon CH3 bond, the one shown here, and we're forming an HH sigma bond in the molecule H2. On the screen, we have our bond association energies, and so we can now apply those. We note that the primary CH bond has a bond association energy of 98 kilocalories per mole. So we're going to use kilocalories per mole as our units here. The hydrogen methyl bond, that HC sigma bond, is going to be 104 kilocalories per mole. If we total those, to break bonds, we have to put energy into the system. We're going to have to put in a total of 98 plus 104, or a total of 202 kilocalories per mole. We have to put in 202 kilocalories per mole to break those two bonds. We can do the same thing over here on the formed side. We notice that the CH2-CH3 bond down here is going to be the best bond to use, and so that is 85 kilocalories per mole. The hydrogen-hydrogen bond is the one up here, and we note that that is 104 kilocalories per mole. Since these bonds are forming, the amount of energy that's going to be released upon bond forming is this 85 plus 104, or a total of 189 kilocalories per mole. So we're going to be putting in 202 to break the bonds, 189 is going to be released, and so we can calculate delta H by subtracting the released energy from the energy that was put in. 202 minus 189 is going to give us a delta H of plus 13 kilocalories per mole. This would be a reaction that is not favorable based on delta H because we have to put more energy into the system to break the bonds than we get out from the bonds forming. And so on the basis of delta H alone, this would not be a favorable process.